Oh, I didn't see you there.
It's sugar.
All right, so like I promised you guys yesterday, I was going to show you guys how to do another type of limiting reactant problem. So why don't we go do that right now?
All right, guys, I made it over from my piano. Okay, so let's go on to example number 2. And I know I told you guys yesterday that I was gonna do this and put it in your guys' Teams or load it up to YouTube, but unfortunately, these videos take a long time to upload and to actually compress them and do all sorts of things. So I'm gonna try to get them out as fast as I can, but I think this is where we're at right now. No big deal, but I'm getting better at it, and we're going to see how it goes today. So here's our problem. So how much carbon dioxide is produced when 25 grams of glucose and 40 grams of oxygen gas is used in a combustion reaction? Now, some of you guys have taken biology or AP Bio can already identify this as not only just a combustion reaction, but a very specific combustion reaction. This is cellular respiration. It's how our body metabolizes glucose to produce energy for us. And you know that two of those products, we've learned that most combustion reactions produce carbon dioxide and water. And we know this is the two products for cellular respiration. Okay, so what they're tasking us here, what I'm testing you guys with, is trying to figure out how much carbon dioxide is produced when you use 25 grams of glucose and 40 grams of oxygen gas. So the first thing that we got to do is we have to figure out which of those two reactants is the limiting reactant so we get an accurate view, right, or an accurate quantity of how much carbon dioxide is produced. We need to get the accurate theoretical yield, because if we use the one that's going to be produced in excess, it's going to predict much more or more than can actually be made. Okay? All right, let's get started. So the first thing we're going to do, like much of these things, is we're going to convert the grams of glucose and the grams of oxygen into moles. So we're going to use dimensional analysis and molar ratio. We have 25 grams of glucose, C6H12O6. That's the littlest 6 I've ever made in my entire life. And our conversion factor here we're going to use is molar mass. So for every 1 mole of glucose, we have 180, glucose is thick, 180.06 grams of glucose, C6H12O6. All right, when I do that and I use my dimensional analysis, cancel out these bad boys right here, and I get 0.139 mole of glucose. I'm going to do the same thing for oxygen gas. Oxygen gas, let me erase that because that looks ugly. All right, I have 40 grams of oxygen gas over 1, right? For every 1 mole of oxygen gas, I have 32.00 grams of this stuff. Okay, so now I'm going to cancel it out, and I get a grand total of 1.25 moles of oxygen gas. Okay, so we converted now both of our masses to oxygen or to moles, right? Sometimes when you get one of these problems, you'll be given the moles instead of the grams. If that ever happens and you're on a test, just stop for like 2 seconds, put your hands together, say a little prayer, say thank you for whoever wrote this test, or you don't have to pray, you can just do whatever, right? Thank you for whoever wrote this test for taking out a very, very, error-prone process, error-prone part of this problem. Okay, so but I didn't because I want you guys to get the practice. So I'm going to write it up here like I did before. So I have 0.139 moles of glucose, C6H12O6, and I have 1.25 moles of oxygen gas. Okay, I'm going to erase all this stuff so I have space to do my problem. Yesterday when I went to go watch the video again to make sure there wasn't any errors, which there were a lot. I don't know how many times I called the reactants the products. But there was one spot in which I left like a little mark, but it was just perfect where it looked like it was a negative sign almost for one of the moles for one of the one of the reactants. No one asked me a question, so I'm assuming that no one thought it was a negative. Okay, so the next thing I'm going to do is I'm going to write a balanced chemical equation, because remember, we're going to be using molar ratio to figure out which of the two of the reactants is the limiting reactant. So listen, I just know what cellular respiration is. I know that it's for every 1 mole of glucose, C6H12O6 plus, I'm going to write this a little bit lower. This is actually like my 7th time trying to do this video. I'm just letting you guys know right now. It's been a process. C6H12O6 plus 6 moles of oxygen, not carbon dioxide like I thought. They're going to react and produce 6 moles of carbon dioxide plus 6 moles of agua fina, or water. Okay, so I learned how to use the laser pointer too. All right, so as you can tell, we have for every 1 mole of glucose, we have 6 moles of oxygen gas, and they react to produce 6 moles of carbon dioxide plus 6 moles of water. Okay, so here's a reaction. It's all balanced out. The coefficients are all there, right? And we see our ratios that we have. All right, so the first thing we're going to start off with is we're going to try to figure out which of the two is the limiting reactant by using these moles and using molar ratio to figure out which of the two is going to run out first. Now, I know I told you before in the past, I said, listen, 75% of the time, if I just look at the coefficients and look at the larger coefficients, I know that's the one that's going to run out first, okay? In this case, oxygen has a coefficient of 6. I'm here to tell you that this is not an example of that, right? And this is why it's important to be able to do this, right? If you're in a pinch and you're in a hurry and you kind of just know, yeah, that's fine. You can use that. You can use that method, right? But it isn't 100%. I'm telling you, it's 75% of the time. So you play with those odds for what you will, right? But I'm just telling you that from my experience, sometimes, right? But you're better off doing it this way if you have time, especially if you have time, right? Hopefully you'll never get stuck on one of these problems. I'm teaching you now so you don't get stuck. Okay, so let's continue. All right, so the first thing I'm going to do is I'm going to look at glucose, and I'm going to see how much oxygen gas it takes to completely use up all the glucose that is in this reaction. So the first thing I'm going to do is I know in this reaction I have 0.139 moles of glucose, right? And in order for me to react that, right, the ratio here for oxygen to glucose, if I'm using molar ratio, would be 6 to 1. So I'm going to multiply the amount of moles times 6, which in this case is 0.139. When I do that, I get a grand total of 0.834 moles of it. All right, so is possibly glucose my limiting reactant? Well, we have 0.834 oxygen is used, right, if I completely use 0.139 moles of glucose. Well, if we look at how much moles I added to this reaction of oxygen, I had 1.25. There is excess amounts of oxygen, all right, which means that potentially glucose is my limiting reactant. I won't know for sure until I do the other part, but for right now I know, right, that in order for me to completely react all of the glucose, I only need to use 0.834 oxygen. So in other words, glucose in this example is going to run out first. Okay, so let's do it now for oxygen. So oxygen, I'll put a little arrow here. Actually, I'm going to erase that a little bit. That looks gross. Ugh. I'm under no pressure to make this look pretty just yet, but eventually, because, you know, I wanted to make it look nice. I wanted to. All right, so in this reaction, I use 1.25 moles of oxygen gas, right? Use my molar ratio. I know that my molar ratio for glucose to oxygen is 1 to 6. For every 1 mole of glucose, I use 6 moles of oxygen. So I'm going to multiply that times 1.6, or 1 over 6, sorry, 1 over 6. And I get, let's see, 1.25 times 1 over 6, and I get 0.208. Okay, now let's take a look at this, like we said before. Okay, so in order for us to completely react all of the oxygen, which in this case is 1.25 moles of it, I need to use 0.208 moles of glucose. I only used 0.139. There's not enough glucose. In other words, it would run out first. Once again, we see that it would run out first. Therefore, we can verify that glucose is in fact our limiting reactant. I know what you're thinking, but wait, Mr. Dominguez, right? You told us the one with the largest coefficient is going to always be, I didn't say always, I said sometimes, right? And in this case, this is that sometimes case, right? There's only 1 mole of glucose, but glucose, like we mentioned before, has, is a lot. It's a large molar mass, right? So it's going to run out first. Okay, 0.208 is not enough. Therefore, we know that glucose is our limiting reactant. Okay, now let's move forward. So like we did yesterday, we're going to still predict how much is made from both, just so you can kind of see the difference. So glucose here, or rather, I keep saying glucose, carbon dioxide, right, is in a 1-to-1 ratio with oxygen gas. Okay, so since it's in a 1-to-1 ratio, it's just, I'm going to use up, where was that? Oh, I drew it the wrong way. That's what happened. Okay, let's do it this way. Do oxygen. There we go. Right? And it's a 1-to-1 ratio with oxygen, so I'm going to use 1.25 moles of the stuff. Right? I'm going to convert this over to grams to figure out how much is produced. So I'm going to use, once again, molar mass, right? And my conversion, or my molar mass for carbon dioxide is, for every 1 mole of the stuff, I have 44.01 grams of it. Hey, Coco, or Toby, that was Toby. Multiply across, and I get 55.01 grams of oxygen gas. Okay? All right, but as we established, there's going to be excess oxygen, so that's not our limiting reactant. This theoretical yield is inaccurate, right? Because we have an excess amount of oxygen gas. We will not be able to use the entire 1.25 oxygen gas because there's just not enough glucose to do so. So this is it's a make-believe number. It can't possibly happen. We would run out of glucose before we're able to reach this amount right here. Okay, so now I'm going to go the other way and use glucose as my limiting reactant. All right, so the ratio here, once again, is 1-to-6, or 6-to-1 rather, because we have, for every 6 moles of carbon dioxide, we have 1 mole of glucose. So we multiply this by 6. We multiply 1.39 times 6 rather, because that's how much glucose is used in the reaction. All right, so we take 1.39, how many moles of it? We get reaction, or we get our calculator out, and we get a grand total of 0.834 moles of carbon dioxide. Okay, so if that's the case, I'm going to hide my face here so I actually have space to do this on. All right, there we go. All right, 0.834 moles of the stuff. I'm going to use dimensional analysis, right? And I'm going to figure out how many grams of the stuff is actually produced. Okay, now I was parched. Okay, so grams, I'm going to use molar mass. For every 1 mole of carbon dioxide, I have 44.01 grams of carbon dioxide. Okay, multiply this out, and I get, well, first of all, moles cancel out, and I'm left with grams. I get 36.7 to 3 significant figures grams of carbon dioxide. Do you guys see a difference? I mean, look at this, right? If we were to use oxygen as a limiting reactant, we would have predicted our theoretical yield would have been 55.01 grams of oxygen gas. However, when we use the actual limiting reactant, which in this case is glucose, we get 36.7 grams of carbon dioxide, an accurate theoretical yield. So then the question becomes then, well, if we completely react all the glucose, right? And oftentimes you'll see that in a reaction that says all the glucose was completely reacted. How much excess oxygen gas would you have in that case? Well, in order for us to do that, like I said before, you would first have to convert the amount of oxygen that you actually use in the reaction, which in this case was 0.834, right? Use molar mass to predict how much that is, and subtract it from the original amount that you had. So if I were to do that, it would be almost the same thing. Let's see, let's do, I'll just do it real quick so you guys can see it. The molar mass of oxygen is, I know that, I don't know why I'm looking at it, 32. So take 32.00 over, I'm going to put a little box here so you guys get confused, right? And we get 32 over 1 mole. And when we do that, I'll get my calculator out. Mr. Dominguez, you did not think this through. No, I did not. I decided to add this part at the very, very end. As a director and now producer, I should not be ad-libbing. All right, so see the calculator? It says 26.688 grams of the stuff was actually used in the reaction, right? But I put in 40 grams of the stuff, so what I do is I subtract 40 minus, what did I say it was, 22 something, and I get 13.31 grams of excess, right? So that's how much didn't get used in the reaction. 13.31 grams of the stuff. All the glucose was used up, but there is some excess oxygen left over. So I'm going to erase this so you guys can have it on your guys' PowerPoint and then see it later. Okay, so that's how you figure out another limiting reactant problem. And this time it wasn't the one that had the highest coefficient. All right, guys, I'm going to post this on YouTube. Hopefully you guys use it. And then maybe today we'll have a little in-class or Zoom meeting. All right, peace out, guys.